Today we're going to be looking at speed sensors. And what is speed? Nobody knows.
What a speed sensor is? Something that
What is
just speed?
so? What is speed besides a drug that some people take? What is
How fast something's going.
Yeah.
The speed of something, how fast something is moving.
fast going or the velocity of motion? And how do we measure it?
Yes.
Wouldn't it depend on the item and the type of sensor used?
No, but I'm sorry. What unit is speed in? What unit do we use for speed? Maybe I should put that.
MPH.
Well, that's one form, but what does that mean? So what we do is what? It's always distance per time, right? So it could be like say miles per hour, but it could be inches per minute, or it could be kilometers per minute, or anything like that. So basically, we measure speed and distance over how long it takes to travel that distance, right? So our sensors are not going to give us the actual speed; they're going to give us a unit that we're going to have to figure out how to convert to distance over time, right? So we know what a sensor is by now. Y'all know what a sensor is by now because definitely going to be on test, right? So we talked about position, light. We talked about proximity. So today we're going to talk about sensors that give us something that we can calculate speed with. So the device we're going to be looking at is tachometers, and we'll look at a tooth rotary encoder. We'll look at Hall effect or magnetoresistive. Also, direct current, AC speed sensors, DC speed sensors. These are actually called these are all tach generators. These are normally called tachometers or tach generators.
Get your mic, Sancho.
It ain't my mic, dog.
Yes, it is.
Yes, it is. I'm getting feedback.
Are we okay?
Uh-huh.
Then we'll look at our. Then we'll look.
She couldn't wait to say that.
Then we'll look at our incremental encoders, which we'll look at the optical ones, which is the one we looked at so far. But the incremental encoder that I'm going to show y'all actually uses a Hall effect. So this is one method. We have one of these. I don't know if Mr. Sanders has it over ACDC machinery side. But what we do is we just put a reflective light. And then what type of sensor would this be? Bounces light off the object itself. Starts with a D. Have you ever saw Barry Miller's Day Off? If y'all haven't, it's a really funny movie, and sometimes y'all remind me of that. So it starts with a D. We know it's a photoelectric sensor. We only got three. We got a through the beam.
Diffused?
Yeah, this is a diffuse sensor. So what it's actually doing, it's going to come over here, but we're controlling the view of what we do by putting a little cellophane. It's usually like aluminum foil or something that we consider highly reflective. So every time this reflector comes, this highly reflective comes back, what it'll do is bounce back, and then of course that only gives us pulses, right? You understand? And then we would have to somehow convert that over to a speed. This is a variable reluctance tachometer, also called a tooth rotary encoder. And what we do here is what's required to induce a voltage magnetically. What do we need? We need three things.
Movement.
This is on the test. So what's the three things we need to induce a voltage? Nobody out there knows?
Relative motion.
Okay, so relative motion, thank you. That's actually the last one.
Conductor.
Okay, we need a conductor. And what do we need?
Come on.
You come on. You the only one seem to know.
Magnetic field.
Magnetic field.
So here we got a magnet. Here we've got a conductor. And now all we need is what? Motion, right?
Relative motion.
Yeah. Relative motion means we can move the magnet or we can move the conductors. Here the conductors are stationary, so we're not doing that. The magnet appears to be, but what happens is we know that magnetic fields concentrate through metals, right? You understand? So every time this tooth comes around, it concentrates the magnetic field. Now we have what? We have motion, and we get a little pulse out of this wire right here. And then when it gets into the trough, it's not near as strong, and then it hits the pulse again. So what we would do is we'd get a pulse for every watt, for every tooth. These are very popular. These are usually used on your car for your anti-lock brake system. They're very reliable, and all we have to have is just a tooth gear out here that this thing flies around, right? A variable reluctance encoder, Vantage, their mature technology. It's been around for a long time. In fact, the first speed encoder that I ever ran into was one of these guys. We had it on a unit at a U.S. Steel where we used to sense the speed. Operate at very high temperature and disadvantage. They cannot measure real slow speed. So this is the problem we have because it depends on relative motion. So if the teeth don't move around fast enough, it don't create enough relative motion to get a high enough pulse out of it so we can actually detect it. So that's the only disadvantage to this. Are we okay? This makes sense?
Yeah.
Yes, sir.
Okay, so this is a variable, basically variable reluctance. And guys, you notice most of these sensors look the same. A capacitive sensor will probably look like this. An inductive sensor will look like this. The only big difference is the front of this will probably have a metal foil on it instead of a plastic foil, which is what your inductive and your capacitive would look like. This is a Hall effect, or this could also be magnetoresistive, and this works on basically the same principle as the variable reluctance. So what is a Hall effect sense? I mean,
Magnetic field.
yeah, they sense magnetic field, yeah. So what we're doing here, but it also senses the strength of the field, the way it's set up here. So this was the example we used on the Hall effect. So here on this sensor, we have a magnet behind the Hall effect, and then the Hall effect is right here. And then, of course, when the wheel spins by, teeth concentrate the magnetic field, which would cause the output of the either magnetoresistive or Hall effect sensor to change. And of course, this would give us a pulse for every gear, which we could come in and actually somehow measure that and get that over time, right? Everybody okay?
Yeah.
Then we run into our tach generators. These basically are just so what determines the amount we get. So a tach generator is basically has a permanent magnet on the outside, so we don't change that. And then we have a rotor in the center. And if we actually looked at it, and I don't think I've got one we could see, but what it is, it's got magnetic poles on it, and then it's got a bunch of wire. And then we bring the wire out to a unit that we call a commutator, which is nothing but slots. And then we have brushes that wrap onto this thing. Now, what the commutator does, and we showed y'all this in class, normally if we spin a coil in a magnetic field, we get AC. But if I was to have a switch, and every time I moved it through there, I would switch it, then we could get a DC out. So basically what the commutator is doing, when this coil spins through the magnetic field, this constantly switches it to make one of the brushes always plus and the other one always what? Minus. And basically, so what determines it now? So I have a magnetic field. There's always a north and a south. And then I'm spinning a conductor through this. So what determines the amount now? So we got a magnetic field. We've got conductors that we're spinning through the magnetic field. So all we like now is motion. So we have a magnet. We have a conductor, right? Now what determines the amount? That's what we need to do. Strength of the field. The number of conductor loops. Or some people say coils. Loops in the coil. And then, of course, 3 would be the speed of the motion. So we can't change the strength of the field. That's fixed. We can't change the number of conductor loops because that's fixed. So if this thing spins faster, it's going to generate more voltage. If it spins slower, it's going to generate less voltage. And the voltage we get out of the tach generator, the DC tach generator, would be directly proportional to the speed. So we could calculate a transfer function. We could say, okay, I get, 15 volts at 100 RPM, right? So we're getting volts out. And then we could calculate the transfer function. And then once we get the transfer function, then the voltage would mean something to us, right? Y'all understand that? Everybody okay? Yes, no?
Yeah, we okay.
Yep.
So this is my tach generator. Let me bring up my camera. Have to do that. Okay. So basically, I'm using just 2 DC motors. I have this one I'm using as a motor. So this is hooked up to my power supply. And this is my tach generator. So what I have is I have my motor hooked up. I'm gonna turn on my power supply. And you see right off the bat, my generator is putting out a voltage that's proportional to speed. So when I increase the speed of my motor, then the output of my tach generator goes up. I think this is a 12-volt motor. That's as fast as we should run it. So we're getting about 9.4 volts out. Now, guys, I wish I had my tachometer here so that I could give y'all the speed that it was running at. But you can see this is really, really easy way to come in and get a measurement of speed with voltage. So once we get our transfer function, of course now the motor is not running at all, I get 0 volts out. And even though it's running extremely slow, we still get a voltage out. So we can precisely, our control system can precisely control the speed of the motor by using this coming in, right? We would call, so what's a closed loop system? It's also called a servo system. What are these systems?
One gives feedback.
They give
the
feedback.
Yeah, they
closed loop.
we have our
Closed loop gives feedback, and the
but
open loop is
at a set point, and then what it does is it looks at the feedback, and the feedback don't match, then it does something to the output to try to cause the feedback to match, right? Okay.
yeah.
DC DAC generators, they're really reliable, they're real rugged. But the problem is, if I want to bring this into a computer, we might have a little problem. We would have to go through some type of D to A converter, right? So this is really what's really neat about these DC DAC generators. They are linear. So if we were to measure the voltage and we knew the speed, you notice this right here varies in a straight line. Okay. Since it varies in a straight line, it's very, very reliable as the speed sensors. These are the speed sensors that US Steel used on number 4 galvanizing line. And that line must have had, good gracious, must have had 100 motors on it. And they use these DC DAC generators that would be that get a dual shaft motor. And so these motors, you can buy motors different ways, but it had a shaft coming out where it was hooked up to the gearbox, and then it had a shaft coming out the back where they hooked the DAC generator at. So these things produce a DC voltage that is proportional to speed. As speed goes up, the voltage goes up. As speed goes down, the voltage goes down. Of course, most of your PLCs have it's available. If it's not included in the programmable logic controller, it's an option that you can get that has analog inputs, which we could take the output of this DC DAC generator and then run it through some math with our PLC, and then come up with the actual speed. This is basically what I just showed y'all. Normally what we would do if we wanted to feed this into a computer, we would have to run it into an A to D converter. And this is a 1, 2, 3, 4, 5, 6, 7, 8 bit. So what we would do is we'd get from 0 to a count of 255, representing the speed. And then we would have to figure out a transfer function for that. But right now, this would indicate that the motor's running at maximum speed. And of course, if we got all zeros, it would mean it's running at minimum speed. Now, if you program these things with a programmable logic controller, this is the type of A to D converter that the PLC has in it. And what it's going to do, it's going to give us a binary number that's equivalent to the speed. And then what we would have to do is we would have to figure out a transfer function to figure out what number represents what speed. The Micrologic 1100s that we have, these have a 10-bit A to D converter. So that means they would go 2 to the 10th minus 1 would be 1023. And then the Siemens PLCs we have, the 1200s, they have a 12-bit A to D converter. That'd be 2 to the 12th, which would be 4095. I'm not doing this in my head, guys. I've been dealing with these so long, I know these numbers. So the 12-bit would have a better resolution than the 10-bit. So let's say we got a 10-bit A to D converter. So that would be the maximum count I get out, and I'm gonna put a voltage coming in. and let's say 10 volts equals max speed. Let's say it equals 100 RPM. So what would that mean? So what count would I get out? I'm sorry. Let's say at 10 volts, because we know what it'll be. So that'd be max voltage would be max speed. So my count would be this maximum count. Okay. So what would be my count per volt? I'm waiting.
100.
Well, it can't be 100 because we're gonna divide it by 1023. So what are we putting in? So it's gonna be 10 divided by 1023. What does that give us? This will be steps per volt. This is what we're putting into our computer. So step per volt. So what would that give us?
Capri, what would they give us?
Just type
Oh
it.
no, I ain't.
Y'all don't have your calculator? Don't y'all have Windows?
9.7 milli.
Yeah, that's what I got.
Now the problem with this is that these steps can't go in between. So what we're saying is, if I put 9 millivolts in this thing, it wouldn't do a step. So an ADD converter is going to look at steps. So on this, each step would be since it's 9.7 would be 10 millivolts per step. That makes sense? Now these guys go in steps. So that would be like an integer. What's an integer? So when we're talking about math, what's an integer?
The number that is raised to.
Now what's an integer?
What definition?
Not a fraction.
Yeah, a number without a fraction. These are called what?
Integer.
No R here though. Sorry. So this is basically what we're getting out of our A to D. So if I'm dealing with integers and then I calculate, what did we calculate? 9 point something. Well, there's no such thing as a 9 point something integer. And so what our A to D converter out is it's giving us integers, but it only switches between steps. So that means if I come up here and put 2 millivolts on the input, this thing would still show me what? Show me 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then when it went to 10, it showed me a 1. And then all the rest of them would be 0. And the next one would switch at what? Then this would be 20. It would give me this. And then it would give me this. So this guy is going to switch every 10 millivolts. It's going to switch because it can't do 9 point what? What y'all come up with? I forgot. Did I call it right? Didn't y'all get 9 point something?
9.7.
9.7.
Yeah. So 9.7. This guy would not see 9.7. So these guys on these ADD converters, they only switch at certain spots. So and they're not rounded either, guys. It has to exceed the step. So that means these guys cannot switch at 9.7 milli. So they'd have to 2 watt. I'd have to switch at 10. And then when it got up to 1023, it means we were putting 10 volts in. So now this other one, if I did that one, then it would have switched before it got to 9.7 milli, right? You understand? So the more counts you have, or the more bits you use for your A to D converter, the more precise or the better the resolution it is. So this guy right here would have a better resolution than this guy right here, right? That makes sense. If I wanted to precisely measure my speed. And then as the voltage goes up, the count would go up. I'm pointing at this with my finger, and I know y'all can't see. So if the voltage goes up, the count would go up, and as the speed goes down, the count would go down. And if you can't calculate the transfer function, then if you were in a PLC and you got a count of 537, that wouldn't mean anything unless you figured out that 537 was 800 RPM. So all right, good job. This is an AC tach. We have an AC tach right here. This was some of y'all that's been around for a while, like me. Used to have floppy disks, and we had an 8-inch floppy disk, and we had a 5 1/4, and we had an 8-inch floppy disk, then we had a 5 1/4. And this is the actual motor right here that ran the floppy disk. And the way it sent speed, it's actually got 2 things in it. You see it's got 4 wires coming out of it. So this is the motor that would actually run the speed of the floppy disk. This is an AC tach generator. So this is going to give us AC out. So I'm going to hook this up. So this is the motor. By the way, one thing we can't figure out with a tach generator is which direction the motor is running. So that's one disadvantage of using these. So if you're going to have to sense the motor's direction, then you would have to combine this with some other type of sensor. So I'll come up here now is put my meter on the output of my tach generator, which is green and red. I'm sorry, green and yellow. Try to keep these things from touching. It's measuring 0. What's my problem? Wait. Anybody got any ideas? So what I'm doing now is I'm measuring this. And this gets people killed. So this is very important that you understand this. Is that I'm measuring AC. What would be the DC average of this right here?
0.
0. So my problem is I have my meter on DC. So what's happening is for every plus we have over here, we have a minus over here. So if this is a plus one, then this would be a minus one. DC gives you the average DC value. And this is why in AC we can't use the average. We use something called the root mean square, RMS, which is the root of the means of the squares. And when you take AC, you'll learn that. So we have to come up with a different way of measuring AC. So since I've got my meter on DC, it's showing 0. So you can see right there, it says, look, see that DC. I'm going to put my meter on AC, and we see that there's something there. So this has got people killed, especially on these meters where you got to press a button to change it between AC and DC. Because normally it'll come up in one voltage level. So guys, you need to really, really be careful on that. Because just because you measure 0 in something, you need to double check and make sure if you're measuring an AC circuit, you need to put it on AC. So here's AC. So this guy's putting out about 3.3 volts. And if I increase the speed, the voltage goes up. I think this is. And of course, if I decrease the speed, the voltage goes down. This motor takes very little. So notice it runs on the real low voltage. If I stop it, it'll stop. Because why? And then I got to put more voltage on it to get it started. Because we got anything that's at rest wants to do what? Stay at rest, right? Okay, so I'm gonna move this guy. And what I'm gonna do is I'm going to hook up my oscilloscope to this so we can see the output. So what the advantage of a sorry guys. Okay guys, y'all take a 15-minute break. I got a malfunction here. So
All right. Everything okay over there?
I'm fine. It's just that I dropped it and I can't let I was going to get it up. So y'all go ahead and take a break and we'll come back and finish this up. Okay?
All right.
So when we swing a conductor through a magnetic field, it's going to generate AC. And originally, the generators on your car were DC generators because they wanted it to come directly out. This is before we had a means of actually taking AC and converting it to DC. It took them a long while to do that. So the problem is that we needed to have something in our car to charge our battery. This is when we started cranking them with a starter. Originally, they used turn cranks where the people would get out there and actually crank them with their hands. Eventually, they finally added a series motor on there, which we could start it electrically, but we needed to do that with a battery, and then we needed to charge the battery. So they did that with a DC generator. So, and we looked at this a while ago. So a DC generator, if I'm going to swing a magnetic field through that, and this is always a north and this is always a south, then what we'll get is an AC. So what they had to do is, one thing they had to do is the rotor had to be wound for one thing. The rotation part had to be wound. So that's where we had to get our power off a rotating magnetic field. And what they did is they, at the back of the generator, they would have these little slots, which would mechanically keep switching this. So what we would do is we would get DC out of them instead of AC. So the problem is number one is these guys are going to be more expensive, of course, because of all the stuff that's required. we have to get our power off a rotating field. We have to go through this thing called a commutator, which basically mechanically keeps switching the output, even though the generator itself is trying to put out AC. So eventually we came up with these devices called diodes. And this is the symbol. And these are our check valves with electronics. And this gave us the ability to take AC and rectify it into DC. So these guys are our one-way valves. So even though we're putting AC into it, what we would get out over here is we would come over here and I'm sorry, let's turn it the other way. I'm gonna bring my AC in here. Well, what we'd do over here, we would get this stuff right here. Because it would only it was a check valve, so it wouldn't let the negatives come through, it would let the positives come through. But then we could combine them in different arrangements. And then we came up, so they call it in your, and if you take solid state, you'll learn how we do that. Then we can take this out and then filter it, and then we can get DC out of it. So once we got in AC generators, what we can do is we can come over here and use our coil right here. And then what we can do is we can spin our magnet. And now we're not trying to take our power off of something that's spinning. We're taking our power off of something that's stationary. Now, what we do, of course, is we make this an electromagnet. Now, what advantage does an electromagnet have over a permanent magnet?
You can change the strength.
Yeah, you can change the strength, right? So we can turn it off for number one, and we can change the strength. So what we do is we take the output of this, we take the output of your alternator now in our cars, we run it through a rectifier, we get DC out of it. Then we have what we call a regulator that's looking at the output. If the output goes down, it increases the strength of the field. If the output goes up, it decreases the strength of the field. So this is what our regulator does. So what we went to now is we went to alternators. So what advantage does an alternator have? Well, number one, it don't have to have that commutator. It don't have to have, it's got to have brushes on it if it's electromagnet. And we're not trying to take our power off a moving part. Over here on our TAC generator, though, we are using a permanent magnet. So all we're doing is we're spinning a permanent magnet, north-south, and then up here we have our coils. Because we don't want to change on a TAC generator, we don't want to change the strength of the field. We want it to be controlled by the speed of the motion. So these things are going to last a lot longer. We don't have that commutator back there we got to worry about. What happens is these brushes are made out of carbon, and of course they wear down as they're running against something that's in motion. Eventually the brushes will wear out, and then of course then your TAC generator wouldn't be any good. These guys right here, these AC TAC generators, they'll basically last forever unless you go out there and you physically do something to break them. So AC TAC generators are cheaper. They're more reliable. They last longer. DC generators are still out there, but usually in older ones, because once we got the ability to take AC and turn it into DC using these rectifiers, then basically DC TAC generators just are not used that much anymore. But that's not going to say you're not going to run into them, because some of you guys work at plants that's been around for a long time. And I learned a long time ago, manufacturer's not going to change something that's working. So if the old way is still working, then they're going to use that. Now, new stuff is going to come in. They're probably going to use TAC generators, AC TAC generators, or they're going to use optical encoders. The preferred method now for using programmable logic controllers is to use a incremental encoder. But what's nice about this guy, we could use two things to indicate the speed. We could use the voltage output. Now, if I needed DC, I can just take that AC and convert it into DC. Or I can use what we call the frequency, the rate of. So any questions on AC tax? Are we okay? Pretty neat. So all we do is we mechanically connect the shaft. Now this is internal. So it's got a motor back here, and then the AC tack is, and this was used by a 5 1/4 inch floppy disk drive. In fact, we stole this off there when we got rid of those things. And this, so it was using the AC tack to make that thing run at the right speed. I think the speed on those is 300 revolutions per minute. They ran at 300 RPM. And the way we calibrated the speed was really, really neat. I wish we still had one so we could show y'all. So we would come in and we'd actually calibrate the speed to make it run at 300 RPM. And you could tell when the speed was wrong because you might have a disk that would work into one drive, and then you move it over to another one and it wouldn't work. Now, probably the problem was the one drive was not calibrated for speed. So it's pretty neat. I'll take a hard drive apart for y'all one day and let y'all actually look at it. I think I've got 2 in here. I take them apart for the magnets. The magnets are really, really, really strong. So if we come back in class, I'll bring some in and put them together and let's see who can pull them apart. But anyway, so AC tax. So we have DC tax, which are still out there. You can still buy them, of course, but popularity, we're moving over to AC tax. This is why they went to an AC generator in your car, which we call an alternator, because they had because AC generators are better than DC. They last longer. We're not trying to take the power off something that's spinning. We're taking the power off something that's stationary. Now we still have to have we have what we call slip rings, where we bring the DC voltage into the spinning the rotor so we can actually control the strength. But AC alternators last pretty good long time too, and they cost a lot of money too. Anybody had to replace an alternator here lately?
Yeah, I had to replace 2.
Yeah, and it's usually just the brushes. So what they have to do on an AC alternator is they have slip rings on the back, and they're usually mounted horizontal like this. And then they have 2 brushes that ride on it. And what these 2 brushes do is each transfer information, transfers the DC into the rotor. But it's not going to be as near as much current as we're trying to get off the stationary part, right? So what usually happens is these brushes wears out. So normally you take that thing in and you have to, they want you to trade in, right? They call it a core charge or whatever, and you bring it in and they give you a little bit of money off that thing. And then normally they send it off and then they replace the brushes. I had a Dodge van that I had, and the alternator went out on it, and it was the brushes. I could see them, and I went to the parts place and I got the brushes for $2. How much would the alternator cost?
Oh yeah, probably about 150 or more.
The problem is they usually seal them up so good now. They usually put the rectifier assembly, everything in there, and they seal them up so good that you usually have to have special tools to get them apart. So they're not as easy to fix as they used to. But normally it's just the brushes that's wore out on the alternator. So here we could go V to F converter, F to V converter. That's nothing but a rectifier assembly. So we could take this and convert it to DC real easy. So anybody who takes solid state, y'all learn how we do that. So incremental encoders, we're already familiar with these because we know that incremental encoders we can use to measure. We can use it to measure position. If we have a quadrature encoder, we can use it to measure direction. And then, of course, what we're going to look at now is how we can use these things to measure speed. So when computers, this is what they like, because these things give us digital out. They give us a digital pulses out that we use. We can represent speed. Most of your PLCs, by the way, support quadrature encoders. So not only could you use them for speed, but you could also use them for position. So we looked at this already, right? Now what we need to do is be able to take a, let me turn off my motor. Okay. Okay. We're going to have to be able to take the rate of the pulses and convert them into a speed. So we're going to have to figure out a transfer function. This is not on this test, and we'll go back over it before the next test, but we have basic formulas to calculate this. For one thing, when this thing spins, so this thing's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's got 15 blades on it. Okay. So what would happen on my sensor here, which is probably a through the beam sensor, right? What would happen on there is that for every 15 pulses, so 15 pulses is going to equal to 1 revolution, right? Everybody okay? This makes sense. So what we'll do is, if I can do the time between one pulse, so we get a pulse for every one of these, we'll get a pulse out. Now, of course, if this is a incremental encoder, if this is a through the beam, then every time a blade comes around, we would get one of these. And they would be at a constant rate if the motor is running at a constant speed. So right here, and normally when we look at time, we don't worry about what's going on here or here. We look at one edge. So between this negative going edge and this negative going edge, this time right here would tell us, would represent the speed, right? Now follow me so far. So
Yeah.
the faster the motor runs, the less the time would be. The slower the motor runs, the more the time would be. So if the time goes up between the pulses, then speed's going up. If the time goes up between pulses, it means speed's going down. If the time before pulses, did I say that right, goes down, then it means the speed is going up. So what we would do is that and we're going to do an oscilloscope, and what oscilloscope does is oscilloscope measures time. So this will probably be the formula that we'll be looking at. By the way, if I want you to do this, I'm going to give you the formula. So this is not a formula you'd have to remember. It's going to be a formula you would have to know how to use, right? You understand what I'm saying?
Right.
Because this is available all over the place. And the only time this would really come into play, if you was programmable controllers and you was bringing this incremental encoder in to a counter or something, and then you wanted to convert that over to RPM. And I'll try to do this. When I get my PLC hooked up, guys, we'll actually play around with some of these things and let you see, and it'll probably make a lot of sense. Are we okay so far?
Yeah.
So my incremental encoder, let's go back and look. So we've already, this is a single channel. Now the problem with a single channel incremental encoder, we can use this for position and we can use it for speed, but we can't use it for direction. So the rate of these pulses, so every time a blade comes by, we would get a pulse, and the rate of the pulses would be directly proportional. The rate would be directly proportional to the speed. So as the rate goes up, the speed's going up. If the rate goes down, speed goes down. But the problem is that when we talk about rate, then we're going to use something called frequency. So frequency, if the frequency goes up, the rate of the pulses goes up. That would be the frequency. So frequency is rated in this would be pulses per second. So 60 pulses per second, if I was getting 120 pulses per second, then we would know that the speed is up. Everybody follow me?
You breaking up.
I'm breaking up.
You was at first.
Yeah, this happens sometimes, guys. I don't know what to do about that. But just let me know when I can go back and repeat. So if the frequency goes up, it means the speed is going up. If the frequency goes down, it means the speed's going down. So if this right here was 50 RPM, revolutions per minute, then of course this right here would be what? 100 revolutions per minute. That makes sense. Now the problem is that what we're going to measure is we're not going to measure frequency, we're going to measure time. So frequency and time are inversely proportional. So frequency would be equal to 1 over time, and time would be equal to 1 over frequency. That makes sense? So if this was 100 pulses per second, 120 pulses per second, what would be the time between pulses? Well, the time would be equal to 1 over 120. So that would be what, 4.3 milliseconds. Is that right? Somebody check on that for me. No, I'm sorry. This would be 8.3 milliseconds. Somebody check that for me. I'm pulling this off the top of my head.
That's correct.
Okay. So, because I know this because AC runs at a frequency of 60 hertz. We call them hertz, and I know that is 16.777, and so 120 would be 8.3. So it's not that I did that in my head, it's just that I'm dealing with Alabama Power, which does 60 cycles. So if I could measure this, then I can calculate that, right? So if I measured 8.3 milliseconds, I know I want you to know the frequency, then that's going to be 1 over 8.3. Of course, it's 333. We'll round it, which would be 120 pulses per second. So these guys are exactly opposite of it. So if frequency goes up, then time's going to go down, which should make sense. So if I'm doing a task and I'm doing 10 things per minute, right? That would be 10 things per minute. And then if I come up here and do 20 things per minute, it means my time has to go down to 1/2, right? You understand that? The time it's taking me to put the things together. So frequency and time are inversely proportional. Now, what we're going to do is we're going to measure it with an oscilloscope. An oscilloscope doesn't measure frequency, an oscilloscope measures time. And we need to be able to take what the oscilloscope shows us and calculate and see what the speed actually is. So a quadrature encoder, what's nice about a quadrature encoder, we can use it to measure position. We can use it to measure direction. And we can use it to measure speed. So we can use 3 different things. So a quadrature encoder gives us off 2 pulses, but the sensors are all set by 90 degrees, electrical degrees. So depending on this one, so if we call this A and we call this B, then here A is occurring before B. So A is leading B. If we change directions, then what would happen, and we'll see this one on our oscilloscope, is now B would lead A. So what we can do with this guy is with a quadrature encoder, we can use it to count positions. We can also use it to sense direction. And then the rate of the pulses, we could also use that to sense speed. So these guys right here are really, really neat. So this is my motor. It's got a quadrature encoder on it. That's why it's got so many wires. So the quadrature encoder is back here under this cap. And then this is a gearbox. I think it's a 135. I don't know. I have to look at that. So the gearbox, so you know, when I come over and hook this up, so I'm going to come up and hook this up. And so what we have is the black and the white. The black and the red are my motor connections. And of course, black does not have to be, this is two motor connections. This is a DC motor. So what's nice about a DC motor, especially a permanent magnet motor, is we can change direction simply by changing the polarity. So here the red and the black, red black might be, if you hook up negative, positive, it might be counterclockwise or whatever. Now the problem is that we're running this through a gearbox. So y'all can probably hear the motor. You know, hear it. But yet out here at the gearbox is running really, really small. So when I sense the speed, I'm not going to see what the motor's doing. I want to know what the shaft is doing right here, how fast it's running. By the way, I hit my finger with a hammer. You see that? And did it hurt? Yes, it did hurt. This is our quadrature encoder that we're going to look at. Okay. So it's got a 131.25 to 1 gearbox on there. Then we have a DC motor. So black and white and black and red would be where I would hook the power coming in to control the speed of the motor. And then I have to have a power supply for my encoder. So this is the actual encoder, guys, and it's using a Hall effect. So the way this thing is set up, a rotary magnet like this, we should actually divide it like this. And this would be like north, south, north, south, north, south. And what we actually end up with is 16 pulses out of our magnet per revolution. But we're not concerned when we're measuring the speed. We don't want to know the speed of this. We want to know what's going on out here. So this is a torque multiplier. So that means if work in equals work out, then what this means is if torque goes up, the gearbox has got to decrease the speed. So you can hear this. You can actually see how slow the actual the actual motor shaft is running. You can hear the speed of the motor. So to calculate the number of pulses we get here, then what we're going to do is multiply it by the ratio of the gearbox. So that means we're getting 2,100 pulses per revolution, which is pretty good, right? If we only count one of our encoder outputs. So if I only count the A output, but if I was to come up here and count the positive going edge of both encoders, then I could use, if I could figure out how to do that, then that would be 4,200 counts per revolution. If I could count the negative and positive edges of both, then we could really, really, really get an accurate speed. But this is pretty good anyway. This is 2,100 pulses per revolution. So what we do is we know time. So first of all, that would be 2,100 pulses per revolution. All we're going to do is measure the time for one of them. So to get the time per revolution, we're going to take the time and multiply it by the number of pulses we get per revolution. But this is still going to be time. But what I want to do is I want to get frequency. So if I know time and I want frequency, then frequency is 1 over time. So this is what we're doing right here, 1 over time. And this would give me revolutions per second because my time's in seconds, right? You understand? So the reciprocal of that would be revolutions per second. So right here, this would give me I'm sorry, right here, this would give me revolutions per second. So what am I doing now? I'm multiplying it by 60. Now, if you work with these forever, then we could take 60 and divide it by 1200. We'd come up and get that 2100. We'd get that number, and that would shorten our formula down quite a bit. But let's see if we can do this. So what I'm going to do is I'm going to hook this thing up. I got my motor hooked up. So now what I have to do is I have to hook up power to my encoder. So I have another power supply down here on the floor. We can't run, the encoder has a separate power supply because we can't change the speed of the motor, because what we do is we change the voltage going to the encoder. So what I have here is I have an old computer power supply right here. And then what I've done is I'll get it in a minute, guys. So I've stripped them off and coupled this on here. So what I'm going to do is I'm going to hook up the power supply to the encoder. I'm going to run it off an old computer power supply. And we're going to use this color code right here. So my plus, I need to hook it up to the blue. And then my minus, I need to hook that up to the green. And then my encoder output would be yellow and white. So I'm gonna take my scope probe and hook it up to common on my encoder. What was the common? Blue? No, blue. No, green. Let me double check that, guy. Yeah, so common is green. Here's the A output. And of course it's moving around because I don't have my scope reference to it. So let's reference it to it. And then I'm gonna come up here and get my blue input. So we can never do this with a meter. So what advantage a scope has over a meter is that it shows you exactly what's there. So here's the blue. And you can see they're exactly 90 degrees out of phase. Okay. And so we notice now, here's our 0, that blue, so blue is leading yellow. Come up here and change the connection on my motor. I'm gonna try to. Now, yellow leads blue. So I know y'all see the colors, but the bottom one. So what we can do, depending on which one occurs first, this would tell us what direction the motor's running. Okay, so far.
Yeah.
To make it easier, what I'm gonna do is I'm gonna turn off blue. I'm gonna take my motor down so it don't move. what formula we're going to be using. So what y'all need to do is write down this formula right here. We're going to use our stuff to measure time. Then we're going to multiply that by 2,100. And you're going to take the reciprocal of that and multiply that by 60, and that should give you the time. That should give you the speed. Everybody okay? You got it written down?
I just screenshot it.
Everybody got it?
Yes, sir.
So, so what I'm gonna do is I'm gonna turn off this one, and I'm gonna move this down so we can see it a little better. And I'm gonna adjust the speed so it crosses, make it a little easier for us to do. Okay. So what I was trying to do is trying to get the line so we can measure it. Okay. What I was trying to do is trying to get the vertical lines. So I have it on 1 millisecond per division. So this is 1 millisecond. Some of y'all can't see it because it's kind of blurred out. So I have 1, 2, 3 milliseconds. So what would be the speed of my motor? I don't see my calculator, guys. Wait, see y'all got it right. Anybody got it? So it'll take 3 milliseconds. We'll multiply it by 2,100. Then you'll hit the reciprocal key, and you'll multiply that by 60. And once you learn the formula, I got my phone right here. I don't know what I'm thinking about. Most of y'all have calculators on y'all's phones, right? If you don't, that's one app you should download, because that would always give you a calculator. What'd y'all get?
Do you divide it by 60?
No, because what we're doing is when I do that 1 over, so my time I'm measuring in seconds, right? Even though it's milliseconds. Then I multiply it by 120, it's still in seconds. Then I take the reciprocal, it's going to be revolutions per second. So I got revolutions per second, and I want to convert it into revolutions per minute. So how would I take seconds and convert it to minutes? I'd multiply it by 60, right? So it's one, right, over our time, which in this time would be 3 milliseconds. So it's 3 milliseconds times 2,100. Then we take the reciprocal of that, and then we multiply that by 60. Because all our times, our scope measures in seconds. So our rate would be revolutions per second. So what we got? Still waiting.
9.5.
9.5?
I got 85 micro.
It's not going to be micro, but there's no such thing as 83 micro. So let me come up here and bring up my calculator, and we'll do this together. Okay. So I would take 3 milli, right? I'd multiply that times 2,100, right? I hit equal. You got to hit equal, guys, right? Then I'm going to take the reciprocal of that, and then I'm going to multiply that times 60. So
Okay.
0.5.
I don't know why I was making that so harder than what it was, but that looked easy when you did.
It's really easy, right? So
You
here's
did
the formula.
good.
Take the time we measure, we multiply it by the number of pulses we get per revolution. Then but this is still time, so we need to get that to frequency. We take 1 over there. This is going to be per second. We want it per minute, so we multiply by that. So 9.5. Whoever said that, guys, y'all did good. So let's see if that's right. So we can see when it runs around, when it flashes. So I'm gonna come up here and set my watch. We'll set the timer on my watch for 1 minute. And then we'll just count revolutions. It's gonna be hard because it's gonna be, I'll be there in a minute. What do I do? So 1 minute, I'm gonna start it as soon as it comes around and it flashes at me. Right there. There's 1. 2. 3. Now y'all know I can count, right? I'm using my fingers and my toes. 4. 5. 6. 7. 8. 9. And my watch just went off. Good job, guys. So see what we did is we just proved our formula, right? You understand? Okay, what I'm gonna do is I'm gonna change my speed. And what I want y'all to do is, let me bring up this so I can see who's actually sending me a message. And I want y'all to send me a message, or just just send a comment or whatever in the box up there. And let's see who gets this right. So what I'm gonna do is I'm gonna change the speed. I'm still gonna make it break on a line. I'm gonna increase the speed of the scope, spread it out. I'm gonna adjust it so it breaks on the line. Makes it a little easier. Okay, I have it on 250 microseconds per division. I've got 1, 2, 3 divisions. So first of all, you're gonna have to take 250 micro and multiply it by 3. $250, I said right, 250 micro. So what we got?
You want us to put it in the messages?
Yeah, just put it in the message to over there, not on the where you make. Oops, missed up.
On the side?
Yeah, on the side. Just make a comment or whatever they call it. I can't.
I already feel like mine gonna be wrong. Oh.
Trying to figure out how to see the comments. Okay, I got. Okay, so I got it from Zachary, Thomas, Logan, Sancho.
You're hot now, Rich.
Has everybody submitted something?
Yeah.
Got it from Sarah, James, Pretty, David Wright. I'm loaded it on another computer. It's really, really slow. So everybody submitted something? Yes?
Yes,
No?
sir.
Yeah, mine should be in there.
Okay, I'll look at it. It should be. I can't see it right now.
So you finna calculate it, Rich?
No, I'm trying to log in. Log in on another computer. I'll bring up.
So we right?
Well, some of y'all's got different answers. That's what I'm trying to see.
Hmm.
Okay, so we take what? 250 micro.
Sounds good.
Multiply that by 3. Everybody understand why we did that? Yes or no? Then I'm going to multiply that times 2100. Then I'm going to take the reciprocal of this. And then I'm going to multiply it times 60. And 38.1 or 38 revolutions per minute. I think I saw somebody had 36. I don't know what y'all did wrong, but most of y'all did pretty good. Are we okay? Like I said, this won't be on this test, but it will be on the next test. All right, guys, y'all take a 15-minute break and come back and we're going to do the test, okay? All right?
Sure.
All right.
Okay.
Yeah.
Oh, okay. Okay.